The previous video introduced our vocab. What are the types of IMFs? As a quick reminder, everything has LDFs, especially nonpolar molecules. That's the only thing that they have. Once a molecule becomes polar, it will also exhibit dipole-dipole attractions, and if that polar molecule has a hydrogen on an N, an O, or an F, it will be able to hydrogen bond. When we have two different molecules together, we look at what they have individually and what they have in common to determine their IMF types. We need to be able to do this because this is what explains, predicts, and compares all of our physical properties. The first step of almost all IMF questions is state the IMF that each compound or each molecule exhibits by itself. That can help us to explain a property that something might have by itself. It could help us to compare the property that two different things have compared to one another, or it could help us to take some data and to predict what property it might have. And that could be boiling point, melting point, freezing point, vapor pressure, any physical property. When they do that, we will learn, and we have learned, that when we're given data, we use that data to support and to help us understand our arguments. But the first thing we have to do is look at a molecule, look at a formula, look at a compound, and just state what type of IMFs it has. So this slide will ask you to do that 1, 2, 3, 4, 5, 6, 7 times. I'm going to ask you to pause and try that out, and then we'll check our answers. If you paused, then you're ready for this. Water has all three key types. It is polar, it has a H on an O, and it also has LDFs because everything will have LDFs. C6H14 might be a hard molecule to figure out if it's polar or nonpolar, but I want to remind ourselves that if it's only carbons and hydrogens, we can assume and we will use the idea that those are always nonpolar. So that can only have LDFs. As soon as we sneak another element in, it becomes polar and asymmetrical, which is why we can have LDFs and dipoles. When we have CH3OH, we still have LDFs, but the O made it polar, and specifically the fact that the H was on the O and the O was on the H gave us hydrogen bonding. As soon as I start to mix things together, I need one or more words to describe them. Sodium is an ion, water is polar. We call that an ion to dipole. Sodium is an ion, C6H14 is nonpolar. We call that ion to induced dipole. And then when I look at number 1 and number 4, they both had LDFs. They both had dipoles. They both had hydrogen bonds. So not only can they exhibit those attractions towards themselves, they can exhibit those attractions when they are mixed together. So after we have stated our type, then we start to think about our strength. How polar is our polar molecule? That's based upon things like shape and electronegativity, or how strong are the LDFs? And that's based upon a new term called polarizability. Polarizability is how polar can that nonpolar thing become? And it's based upon how many electrons we have. You won't have to explain this at a high degree, but the short version is the more electrons we have, the more random motion we have, the more electron wobble we have, and then our LDFs can become stronger. So we think more electrons makes it more polarizable, which means that we have stronger LDFs. One shortcut is they often will give us the molar mass. This is a correlation, not a causation. Heavier molecules don't actually have stronger IMFs. Heavier molecules have more electrons, which cause them to have stronger IMFs. So as I look at these right here, it's not the molar mass, but it's the added atoms, which means added electrons, that gets our attractions a little bit stronger. The boiling point is what we're seeing across the bottom here. It's going up, up, up as our electrons go up, 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 as our polarizability goes up, 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 meaning that our LDFs and our attractions are higher. When we are asked to compare the IMFs of each thing, we have to start by going back a few slides and recognizing what do they have. Well, C's and H's is nonpolar, so it only has LDFs. H2O has LDFs, dipoles, and hydrogen bonds. By the fact that we've added all of those up means that water is stronger overall. Br2 and I2. We see no H's, and we might think to ourselves, are these polar or nonpolar? But they're a perfectly balanced diatomic molecule. Both of these are nonpolar. So the answer of which one is stronger if they only have LDFs is which one has more electrons, and that is iodine in this case. When we have something like CF4, we might have to draw that out to prove to ourselves that that is nonpolar. Bond, 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 perfectly balanced. When I have CH3F, I have H, H, H with an F. It is not perfectly balanced. This molecule is polar. So I have a polar molecule versus a nonpolar molecule. They both have LDFs, but the CH3F also has dipole-dipoles. So that is enough evidence that we could think it probably has stronger IMFs. We can recognize that hydrogen bonds are special and strong. Dipole-dipole attractions are significant and can be very strong. And LDFs by themselves are temporary and weak. But if we have enough electrons, those LDFs can add up and be stronger and be more significant. And that's where data comes in to help us. When we have strong IMFs, that means we have a high melting point and a high boiling point. That means we have things that are very strongly stuck together, like a solid compared to a liquid or a gas. We have a low, and this one's important to remember because it's the opposite, a low vapor pressure, because very little of our substance is able to turn into a gas. The ones that I don't have in bold here are the ones that we look at the least. That's what we're asked about far less. Volatility is just another way of saying how fast something evaporates, but we normally think of that in terms of vapor pressure. And although surface tension is a cool property that's super important, in chemistry we are not often asked about that in a lot of detail. So when we are asked about our IMFs, sometimes we don't even need to classify which type of IMFs do we have. The stronger the IMFs, the stronger the attractions. Cyclohexane has a boiling point of 81. Toluene has a boiling point of 111. 111 is higher than 81. Ammonia has a boiling point of -33. Methane's -161. Even though they're both negative, hopefully we recognize that -33 is over 100 degrees higher. Iodine's a solid, chlorine's a gas. Well, what is that telling us about our attractions? It's telling us that iodine is strongly attracted enough that it stays stuck together. Chlorine is very weakly attracted and is moving separately and moving freely. Vapor pressure, or VP, is probably the most confusing because it's the opposite pattern, but a high vapor pressure means that that thing can go to a gas very, very easily. A low vapor pressure means that that thing is not going to go to a gas nearly as easily. So we use our data along with our IMFs. As we look at this, we're comparing and contrasting, we're counting electrons, we're looking at properties, and we're just taking everything that we're given and we're putting it together. It'll take in-class practice and repetition, but just like Lewis structures and everything else we've done, we'll get good at it once we know our basics. As you wrap up, see if you can notice differences in these molecules, similarities between these molecules, and understand those similarities and differences.